Good afternoon and warm welcome to one and all present here. This afternoon, we have gathered here for the enrollment lecture in honor of Professor Prakash P. Karat. We are really proud to have you, sir. Professor Prakash P. Karat Endowment Lecture started in the year 2015 by the students and admirers of Professor Prakash P. Karat. Previous 9 lectures held at 5 different institutions, namely St. Aloysius College, Mangalore, University College, Mangalore, St. Agnes College, Mangalore, St. Phenomena College, Puttur, and Mangalore University, Konaji. Well-known professors from reputed institutions delivered lectures. Today, we have the 10th lecture in the series and we are fortunate to have Professor Arumugam Thamizhavel from Tata Institute of Fundamental Research, Mumbai. Colleagues of Professor PPK, senior teachers, students, well-wishers, and admirers of Professor PPK gathered here. After becoming the university, we are having the endowment lecture first time here. Prayer is the center of our works and life. It gives a profound meaning to every activity we do. To begin the program, let us invoke God's presence in the midst of us. I invite Miss Anaga and Co to lead us into prayer.
पे तू चल रबा रहेगा तेरे संग वो तो है तेरे दिल में हाँ तू क्यों बाहर उसे ढूंढता नेकी की राहों पे तू चल रबा रहेगा तेरे संग कभी है वो साहिल पे कभी है वो मौजों पे कभी है परिंदा वो उड़ता हुआ वो तो खुदा है जीवन है राह है उसको न मज़हब में कैद करना वो वफादार है हाँ खुद ही प्यार है साए में उसके सुकून कितना दुनिया का नूर है ना तुमसे दूर है पाकीज़गी में वो है बसता नेकी की राहों पे तू चल रबा रहेगा तेरे संग नेकी की राहों पे तू चल रबा रहेगा तेरे संग.
Prakash P. Karat and Dr. A.P. Radhakrishna to the dais. Let's give them a round of applause. It's a welcome gift to encourage others to achieve greatness. I humbly request Dr. Ishwara Bhatt to welcome the gathering. Sir, please.
You gathered here. First of all, I feel extremely happy to see galaxy of very senior physics staff members gathered here, along with the physics student mostly, plus many staff members from other departments as well, dignitaries on the dais, and respected staff members from various colleges and our dear students. I am here to do the pleasant task of welcoming all of you. But before that, this PPK Endowment lecture, this has been very well said over the last few years. For the last 9 years, we had this program in a very nice way. It is not easy to have such a continuity. And over the years, every year, we used to get very reputed scientists from different pioneer institutes of the country. That way, this lecture series has got its own significance and it has created a wave as if something will going to happen this year under PPK Endowment lecture. That way, all lecturers and senior retired staff members are also coming here. So it is my pleasure to tell you that January 19th onwards, our autonomous college has been uplifted and we got the new status of university, St. Aloysius deemed to be university. I need to tell that under St. Aloysius deemed to be university, this will going to be the first endowment lecture, even though we had 9 lectures earlier. So this is in a way a decennial celebration. 10th lecture today we will have. So we have a very good resource person. But before that, I would like to welcome today's president of this very auspicious special talk series, none other than the new Vice Chancellor of the newly born Saint Aloysius deemed to be university, none other than Reverend Dr. Praveen Martis SJ, one who is supporting all the activities here. A warm welcome to you, dear father. Welcome. Today's resource person, I told you already, over the years we used to get resource person from reputed institutions. Today also we are having one such stalwart from TAFR Mumbai, none other than Professor Arumugam Thamizhavel. He is professor from the Department of Condensed Matter Physics and Material Science, TAFR Mumbai. Sir has come all the way from Mumbai, well in morning only, and he is with us from half an hour back only, and we had the discussion, and he is very happy to see the campus and to interact with the staff members here. So a very warm welcome to you, sir. Well, our own retired professor, when I say our own, from the physics stream, he is none other than Dr. A.P. Radhakrishna, today's guest of honor, retired professor from St. Philomena's College, one who has involved largely in various activities of the Physics Teachers Association, and also he has he was instrumental in bringing so many activities from the Physics Teachers Association over, in different colleges. Sir has agreed to be here today as the guest of honor. A warm welcome to you, dear Dr. Radhakrishna sir. As you know, this program is in the name of Professor Prakash P. Karat Endowment Lecture. When I say Professor Prakash Karat, almost all the persons who are in the teaching line, mostly excluding the very senior staff members, from my side onwards, next generation, we are all students of Professor Prakash Karat, our beloved professor, Professor Prakash Karat. So we got many things taught by Prakash Karat sir when we were in the Bangalore University, and afterwards also. He is very much well known among physics teachers. So on his name this endowment lecture is going on, and we are very much delighted to have you in this program, sir. A warm welcome to you, to sir. I need to tell something about Dr. Chandrasekhar Shetty, who is instrumental in bringing this program for the last many years, the PG Department of Physics. We are doing this together, UG and PG, but his role is a larger role. He is instrumental in bringing this endowment lecture, and over the last 9 years and the 10th year program is going on very nicely today. It is because of the effort of Dr. Chandrasekhar Shetty and all his colleagues from the PG department as well as UG. So a warm welcome to, especially to Dr. Chandrasekhar Shetty. And my special welcome goes to, I don't want to tell the names of all the faculty gathered here, so many are there. Dr. K.V. Rao, Dr. G.G. Prabhu, many faculty, Dr. Pattavi, Vijay Kumar. So if I, Chandrasekhar Shetty sir, and many are there here. Balakrishna sir, Dr. Ganesh, Prakash Kama sir, Vincent, Dr. Vincent from St. Joseph's College. If I forget to tell some names, kindly forgive me, not deliberate. So, but I'm extremely happy to see the galaxy of physics teachers here. So, a warm welcome to you to this 10th Destiny lecture. Welcome, sir. And also, I'm happy to see some faculty from other colleges. Presently, they are working. So, a warm welcome to all of you. And like the students from physics department, UG and PG are here. So, a warm welcome to each and every one of you. And finally, once again, I thank everyone, those who are present here. You are all stakeholders to make this program a grand success. So welcome once again. Thank you.
Notes of welcome. As a sign of cordial welcome, I invite Dr. Ishwara Bhatt to florally welcome Professor Thamizhavel, Professor K.M. Balakrishnan to Vice Chancellor, Dr. Jeevan Pinto to Professor Prakash P. Karat, Dr. K.B. Vijay Kumar to Dr. A.P. Radhakrishnan, thank you. To celebrate the decennial year of endowment lectures, professors, students came up with a commemorative book containing representative chapters of previous lectures. The book titled Decadal Odyssey in Physics, a chronicle of PPK Endowment Lecture Series. Now, it is the time to release the book. So, I request Vice Chancellor of our university, Reverend Dr. Praveen Mattis S.J. to release the book. As we all know, Dr. Praveen Mattis S.J. is an exceptionally dynamic individual and a visionary who thinks creatively with innovations leading our university to a greater heights with his passion truly remarkable. Now I request Reverend Dr. Praveen Mattis S.J. to give his message.
Respected Professor Arumugam Thamizhavel, the resource person of the day, Dr. A.P. Radhakrishna, the guest of honor, Professor Prakash P. Karat, on whose memory we have this special endowment lecture, Dr. Ishwara Bhatt, the convener, all the guests of the days, members of the faculty, and my dear students. I'm extremely happy to be here this afternoon for the Endowment Professor Prakash P. Karat Endowment Lecture 2024 on the topic Crystal Growth and Anisotropic Studies of Strongly Correlated Electron Systems and Topological Semi-Metals. Of course, only physics students will understand that. And I, being the physics student, the first student of Dr. Ishwara Bhatt, I keep saying that because he reminds me of it. And my professors are here, Professor K.V. Rao and others who have taught me here are also part of this very important event. Today I am extremely happy also to release this book, Decadal Odyssey in Physics, a chronicle of the PPK Endowment Lecture Series. It's also released from St. Aloysius Prakashana, edited by T. Chandrasekhar Shetty. So I would like to congratulate Professor Chandrasekhar Shetty for editing this book and also organizing this 10 years lecture series. This year it becomes the 10th year, that's why it's a decadal odyssey in physics. Is a 1 decade of journey, 10 years of wonderful journey that is beautifully depicted in this book. So I would like to congratulate Dr. Chandrasekhar Shetty and the whole team for organizing it. We had 10 wonderful lectures. Today will be the 10th lecture, all in different areas of physics, also frontier areas of physics, and many have already contributed to this series, and our own professors from here and others have combined and worked together to bring out this book. Professor T. Chandrasekhar Shetty, Tanima Mukherjee, Trilochana Shetty, Kumara K, Neelakantan and Rita, Jeevan Pinto, Kiran R, Naveen Mascarenas, Richard Gonzalez and Ita D'Souza, and E. Deepak De Silva. So there are 10 such research articles written by them. The similar themes of last 10 years of lectures. There's a lot of work that is done, a quality work that is done by these faculty members. And I'm very happy that many young members of physics department are involved in this. I think that makes me very happy and joyful that the legacy of the senior teachers are already taken over, or in the journey of taking over and also moving towards the younger generation of students. Their own students are writing these good articles. That's the way it should be, because none of us can remain forever. Is that young generation of the students who become the lecturers, who become the scientists in that particular area and also do research and publish should be the part of our legacy. That becomes joyful journey for all of us. And today being the 10th endowment lecture, but I would like to always thank Professor Prakash P. Karat. They call him with love PPK. And Professor is here always with smile, coming to this institution for several years after his retirement, and also bringing in very essence of science and physics to our college and bringing quality to the physics department. So we are really grateful to you, as they all admire you. Your students are here, and the 5 decades of teaching and then 1 decade here, almost 6 decades of your work is really shown. That is the love that your students are showing, because they're all inspired by you and they're all in great positions. So we remember you and thank you for being such a great and inspiring professor of physics to Mangalore University and to Mangalore region, to St. Aloysius deemed to be university, and all of us all over India and all over the world. Thank you. Let's give him a round of applause. As I said, the legacy and the continuation is very important for anybody to move on in these directions. That's why there are students of now Chandrasekhar Shetty and others are here, the present physics students, and I'm sure they will listen and also carry on this important legacy and see that you all do wonderful physics, because physics is one of the most important departments which takes us back to our own reality, and to understand the reality, it makes it easier. And these are all very important departments. Today, of course, we are again coming back to interdisciplinary subjects and also bring various aspects of them together. So at one point they were all together, they again compartmentalized and worked in silos, but now coming back to again integrated interdisciplinary approach after LEP 2020. Though many scientists like Professor C.N.R. Rao and Kastur Rangan who have come here reminded us several times that we should be working together, should not be working in silos, because when you go deeper and deeper, all these subject domains like physics, chemistry, mathematics, computer science and all come together, and these lectures were all from physics, material science and computer science, and they're all very much connected to the present generation and present times too. With the AI and machine learning and IoT and the things that we are moving ahead, we feel now these domains need to be doing something more and also integrating various aspects. Based on that, today we have got an excellent lecture by Professor Arumugam, Thamizhavel, on the professor from Tata Institute of Fundamental Research, Mumbai, and a very important topic of crystal growth and anisotrophic studies in strongly correlated electron systems and topological semimetals. I'm sure all of us are excited to look forward to this important journey and the lecture, and to see how we can move forward in this direction and also learn something in this area. And I would like to especially thank Professor Arumugam for coming over here. He said it's the first time that he is a St. Aloysius University, but he has come to Manipal, I think, in the past. So warm welcome to you to Mangalore and St. Aloysius deemed to be university. And we look forward to this very important lecture. I thank all of you gathered here for this lecture. Let's all interact and engage and learn from this very lecture and be inspired by it. Thank you. God bless you.
Thank you, Father, for your words of inspiration and wisdom. I call upon Dr. Chandrasekhar Shetty, HOD of PG Department of Physics, to introduce the speaker of the day.
Professor Arumugam Thamizhavel, Professor and Chair, Department of Condensed Matter Physics and Material Science, Tata Institute of Fundamental Research, Mumbai. His areas of specialization: crystal growth and anisotropic properties of rarer intermetallic nacticides, superconductors, strongly correlated electron systems, topological materials, and so on. Professor Thamizhavel obtained his graduation and post-graduation degree from University of Madras. He obtained his PhD degree from Crystal Growth Center, Anna University, Chennai. From the year 1998 to 2005, he was a postdoctoral fellow at Kyoto University and Osaka University, Japan. In the year 2006, he joined as a faculty member in the Department of Condensed Matter Physics and Material Science, Tata Institute of Fundamental Research, Mumbai. At TIFR, he had established a state-of-art crystal growth facility to grow intermetallic compounds, particularly rare-based strongly correlated systems and superconducting materials. Professor Thamizhavel has guided 5 PhD students and 3 are pursuing under his guidance. He has mentored 10 postdoctoral fellowships. He has mentored 10 postdoctoral fellows in his research group. He has to credit more than 250 papers published in various internationally reputed journals. His citation index is 5,377. H index is 35 and I-10 index is 126. Dear friends, humbly I present you Professor Thamizhavel.
Thank you, sir, for letting us know a great personality, Professor Arumugam Thamizhavel. Without further ado, I take this pleasure to invite Professor Arumugam Thamizhavel for his lecture. The time is yours, sir, please.
Okay, so I'm extremely sorry about this technical glitch. I didn't copy this my file into this computer here. I'm extremely sorry about this delay. Anyway, at the outset, I would like to thank the Vice Chancellor and Professor Prakash Karat for inviting me to deliver this endowment lecture here. I am overwhelmed by the hospitality that I have been given until now, and I hope that I will live up to the expectations of delivering an interesting talk to the young generations and as well as to the professors here. So it's a Saturday afternoon and the ambience is too good, so most of you will feel sleepy, but I'll make sure that you don't sleep. Okay? Yeah. So today I'm going to talk something about the crystal growth and anisotropic properties. How anisotropic properties of strongly correlated systems. I think this will not, the pointer will not work here, I think, isn't it? Okay. So I'm Thamizhavel, as you have heard until now, and I'm chairing the Condensed Matter Physics Department in TIFR. Today I'm mainly going to focus on the first part of the talk, that is crystal growth. So why is that? Crystal growth is a branch of science. Crystal growth is a branch of science which has 3 different flavors. It's an art, and it's a science, it's a technology. I think this is not moving. It's an art, it's a science, and it's a technology. It's an art because one needs to have some kind of expertise in growing a single crystal. See, suppose when you're doing some research, you can buy some sophisticated instruments, like for example, if you buy an X-ray diffractometer or an electron microscope, you just put your sample, you get your X-ray diffraction pattern. You just put your sample, you can observe a huge size of your samples that under an electron microscope. But if you buy a crystal growth machine, be it few lakhs to crores, it will not fetch you some crystals. So you need to have some kind of expertise, and you need to master this technology so that you can grow a single crystal. So it's an art by itself. And it's a science. It's a science because you need to know the melting behavior, you need to know the solubility of the material, you need to know the vapor pressure of this material at high temperatures, and you need to know the crystallization temperature. If it is possible, if you know the crystallization temperature, it's easy for you to grow these single crystals. And it's a technology. You can grow a huge size of crystals, like about 200 kilograms of crystals that you can grow. It's a technology by itself. The reason is that now the government is focused, throughout the world, people are worried about these energy resources. So solar cells is a default choice that people are looking out when they are looking out for energies. So silicons, the base of the solar cell is silicon. So if you can grow such a large, big single crystal, then you can produce very huge quantity of solar cells. So if you want to become an entrepreneur, you can choose crystal growth as your topic of research. Okay, so the importance of crystals. So whenever I say crystal, people immediately think that it's something very flashy and it's very attractive and things like that. This is aluminum oxide crystal, which is doped with chromium 1%. And then this is a diamond, carbon, high pressure. If you have pressurized carbon, you can get diamond. And then sapphire, it's again nothing but aluminum oxide with a small amount of titanium and iron doping. And emerald is again an aluminum silicon oxide composition. So these are looking quite beautiful. These are crystals. If you cut and polish it, you get beautiful, this kind of eye-catching jewelries. But this is nothing but this aluminum oxide. If you look at it in the polycrystalline form, you will see something like this, as I have shown you. So these are alumina crucibles, which are using it to hold some of the samples up to high temperatures. So this same material, when you grow as a crystal with some doping, you have beautiful colors, and when you cut and polish, you can have very nice looking samples. The same sample, if it is in a polycrystalline form, it will look like this kind of white stuff, which is shown here. And it's not only, crystals are not used for only aesthetics. And these days, most of the technologies use single crystals. Like for example, your high-end phones, these days it comes with sapphire glasses, which don't break that easily. So this is the facility which is there in US, in one of the companies, where they are making this aluminum oxide crystals. You can see a cut and polished oriented crystal, which is shown there. So the top right one is the raw material, this aluminum oxide. When you grow them as a single crystal, you get such a kind of bowl. On the left-hand side, bottom left, you see an oriented cut and crystal, which looks like this. And from that piece, you can make a glass for your mobile phones. So crystals are there everywhere. And all your electronic devices has one crystal or other. And you have lasers, which are, the main component of laser is a single crystal, non-linear optical single crystals. And for solar cells, anyway, I have told that the single crystals are very much important. And quite a few years ago, about some 10 years ago, there was a huge experiment that was happening in LHC, Large Hadron Collider. People found that the God's particle has been found out. And those things have been detected using this lead tungstate crystal, which is shown just before that man. There is a 1 foot long lead tungstate single crystal, which is shown there. The crystals of that 1 foot long, 76,000 such crystals are used to detect this God's particle, Higgs bosons. So these are the importance of single crystals. So now, having said that importance of the single crystal, let me start with the basic definition. What is a single crystal? Now, there's a motivation for you to know what is a single crystal. And since you are doing MSc in physics, if you take any solid-state physics textbook, Kittel, or whatever that book that you read, if you look at the definition, it will be reading like this. A homogeneous body consisting of a three-dimensional periodic arrangement of atoms, ions, or molecules is a single crystal. So, but if you do research, you think different. So there is an alternate definition. So I used to define it, materials which produce diffraction spots are single crystalline. So that means any material, when you subject to an electron diffraction or X-ray diffraction, if it produces a diffraction spots, then we say that it is a single crystal. It cannot be it can be a huge crystal, it can be a micron-sized crystal. If it produces a diffraction spots, it is a single grain. That means it is a single crystal. So now naturally the question comes to your mind, then what will happen? What is a polycrystalline sample? So the polycrystal is nothing but a very large number of tiny crystallites. So large number of small tiny crystallites constitute a polycrystalline sample. So now I told you that the single crystal produces very beautiful diffraction patterns. So this is a single domain, only one domain you have, and this is the corresponding diffraction pattern that you get. You take an X-ray diffraction, you take an electron diffraction. Depending on the diffraction conditions, you will get a diffraction pattern like this. So this looks very beautiful, symmetric pattern. And I can immediately say that this is a single crystal because it produces diffraction spots. So there are no grain boundaries here. On the other hand, a polycrystalline sample, because there are large number of tiny crystallites constitute a polycrystal, each grain is a single crystal. So now if you look at this right side figure, there are these various grains which are oriented in different directions. So each grain will produce diffraction spots as shown on the left hand side. So but they are oriented in different directions, the spots will be slightly tilted. So if you constitute all of them together, you will see these kind of concentric rings. So if you see the left hand side figure, if you note very carefully at the center, you can see a circle. If you connect all the dots, you will see a circle. So similarly, since these grains which are oriented in different directions are producing diffraction spots at different angles, then you constitute this kind of concentric rings. So you prepare some sample and you think that it is a single crystal, and you do go to an electron microscopist or an X-ray diffractogram, and if you do this electron diffraction pattern, if you see this kind of concentric rings, you can at once tell that whatever the sample that you have prepared is a polycrystalline sample. On the other hand, if it produces diffraction spots, you can immediately tell that it is a single crystal. Okay, let me tell you some example. Having said about this single crystal, what is so important with a single crystal? Why do I bother about a single crystal? Why there is so much hype about a single crystal? So this example will tell you why we need to have a single crystal. So this is an electrical resistivity diagram of a sample which is named cerium-2 nickel-3 germanium pi. This is an intermetallic compound. I measure the electrical resistivity from 300 Kelvin to 2 Kelvin. So I have made a polycrystalline sample. I know that it is not a single crystal, it is a polycrystalline sample. When I measure the electrical resistivity is looking like this. Quite weird, but don't worry about the shape of the crystal. The point which I wanted to make here is that if I grow a single crystal of this sample and do the same measurement on a single crystal, how the electrical resistance will look like. So let's see that. So I have grown the single crystal in my laboratory, and this being a single crystal, and the crystal structure of this compound is orthorhombic. So when I say an orthorhombic crystal, you can immediately imagine that A, B, C are not equal and alpha, beta, gamma equal to 90 degrees. So all these things are in the first chapter of Kittel about the 7 kinds of crystal systems and all these things. So if I say orthorhombic, being a solid state physicist, or if you have studied about solid state physics, you should immediately remember that A is not equal to B is not equal to C and alpha, beta, gamma equal to 90. So when I say A is not equal to B is not equal to C, then the unit cell will be having a different directions along A, B and C directions. When you measure the electrical resistivity by making the contact along the 100 direction. So if you look at the top figure, I have pointed this 100 direction is this way. If I make 4 contacts, current, voltage, current. If I pass a current along the A-axis and measure the voltage, I will have a red colored curve there, which is having electrical resistance at 300 Kelvin. It's about 325 microohm centimeter. On the other hand, I remove the contact from A-axis. On the same sample, if I pass the electrical current along the B-axis and measure the electrical resistance, I get the green curve. where the room temperature, the electrical resistance is about 100 micro-ohm centimeter. And I remove the contact along B axis and I make the contact along the C axis. The same sample, depending on in which direction you pass the current, you have the electrical resistivity values which are different. So this is called anisotropy. So to study these kind of anisotropic physical properties, you need to have single crystals. If you don't have a single crystal, you will get the average of this electrical resistance as I have shown in the left-hand side figure. Okay, so since I am interested in studying the magnetic properties of these materials, these single crystals are highly useful to find out the easy axis and hard axis of magnetization. You know, the magnetic materials have easy axis of magnetization and hard axis of magnetization. Again, if you look at the chapter on ferromagnetism in Kittel, you can see that iron magnetizes relatively very faster even by applying a small magnetic field, and then it saturates. So that is the easy axis. Along 111 direction, it may be a hard axis. So similarly, whatever the sample that I prepare, I can find out the direction, easy axis and hard axis direction in the crystals. So here the susceptibility, where the susceptibility drops down to 0 for chi-parallel direction, that is the easy axis direction. And on the, if I apply the field perpendicular to that, then the susceptibility is almost flat. If I don't have a single crystal, I will have an average of this, which is represented by chi-poly, which is shown by the dotted line on that graph. So similarly, if I do the magnetization on this right-hand side top figure, in the antiferromagnetically state, the magnetic moments, initially they are in the opposite directions, but as I am applying the field along one of the spin directions, at a particular field, critical field, these magnetic moments will try to spin, flip. That means that huge jump in the magnetization is seen, and then it becomes saturated. So this is called field-induced ferromagnetic state. So this is the easy axis for that particular direction, for that particular sample, which is shown in the top graph. So that is all antiferromagnets at high magnetic fields will become ferromagnet because of this field-induced magnetism. On the other hand, if I apply a magnetic field along the hard axis direction, even though if I apply a huge magnetic field, it will not saturate to that level. I have to apply a very large magnetic field, which is not achievable in the laboratory. So similarly, in the bottom curve, depending on the samples, exchange interaction and other material properties, you will see how the spin flip happens. Sometimes the spin rotates very gradually. Sometimes the spins rotate all at once. If it rotates all at once, you will see the sharp jump in the magnetization. And the bottom one, the spins gradually rotates. That's why you see a sharp jump, and then there is gradual increase in the magnetization. Okay, so having said about this introduction to this magnetism and all these things, I have told in my topic, I have given crystal growth of strongly correlated electron systems. Let's come to the strongly correlated electron system. So, you know, these strongly correlated electron systems are formed by the compounds that have F electron shells. That means F electron in there as one of the constituent elements. Like for example, the lanthanide series, which that if you see the periodic table, if you remember that, there are two series of compounds which hangs out of the periodic table. They are not in that 3D transition element or 4D transition element. They are just separate. They are kept aside, they're kept below the periodic table. So those two series are called lanthanide series and lanthanide series. So in the case of lanthanide series, if I see the electronic configuration of lanthanum, it will be like xenon core followed by 4f cell and then 5d1 and 6s2. So lanthanum does not have an F electron. So you have a xenon core which is completely filled followed by 5d1 and 6s2. So these 5d1 and 6s2 are the conduction electrons. That means they move everywhere inside the sample. So if I go from lanthanum to cerium, I'm adding one more electron to the system. That means the F electron becomes 4f1, 5d1, 6s2. And if I go to praseodymium, I'm adding two electrons, 4f2, 5d1 and 6s2. So if I go in the lanthanide series, I'm adding F electrons to the 4f cell, whereas the outer electrons, 5d1 and 6s2 remains the same for all the rare earths. So the outer electrons, 5d1 and 6s2 is the same for lanthanum up to lutetium. So that is why rare earths are trivalent in nature. So they have the valence 3. So Whatever may be the case, only the F shells is getting occupied. The outer electrons remain 3 throughout the series. So, and these F electrons are unpaired. As you can see in the right hand side, cerium has 1 unpaired electron, praseodymium has 2 unpaired electrons. You might have studied any unpaired electron because of the spin and the orbital motion, you have a magnetic moment. So that is what is happening. Because of these unpaired electrons, these rare earth magnets, the rare earth elements show magnetism. So we wanted to study the anisotropic properties of these magnetic elements. And so now, if you see the radial distribution of the 4f wave function, see, there are f electrons which are unpaired. But now the question is that how do they interact with each other and how the magnetism is appearing in this compound. So if you see the radial distribution of the wave function, the 5d1 and 6s2 are extended to a very large value. You can see the dotted curve outside 5d, 6s and things like that. So there is other cerium, one cerium atom is sitting here, the other cerium atom is sitting here. The 5d1 and 6s2 of this cerium and 5d1 and 6s2 of this cerium will overlap and they form a conduction band. The electrons will move throughout the sample. Whereas the 4f electron wave function, they are not interacting. The 4f electron is only very small here and the other 4f electron is very small here. So that means these two f electrons cannot interact with each other. When they cannot interact with each other, how the magnetism is appearing in this compound? That's the question. So you can see that the spatial extent of this f electron is about 0.3 angstrom, whereas the interatomic distance is about 3 to 4 angstrom. The 3 to 4 angstrom is quite large. The 4f wave functions are very, very small. They cannot interact with each other. Then how the magnetism in these rare earths appear? So that is because the famous interaction called RKKY interaction. That means the F electron, localized F electron, which is shown by this arrow, and these small arrows are conduction electrons. There is an exchange interaction which is happening between this local F electron and the conduction electrons. And depending on the strength of this exchange interaction, the conduction electron, since passes the information to the other F electron, which is at a further off place, it will tell, okay, you align in the upward direction, you align in the downward direction. So that information is the rare earth based intermetallic system. This is called RKKY interaction, which is very popularly called as RKKY interaction. And there is another interaction called Kondo effect. So at sufficiently high temperatures, the F electron and the conduction electron, they don't talk to each other. They don't interact at all. But when you come to your temperature region, which is called Kondo temperature, the F electron partially interact. That means they get scattered. And at sufficiently low temperature, below the Kondo temperature, the conduction electrons forms a screen cloud. I mean, there is one F electron. Surrounding that, the conduction electrons are in the opposite direction. So this F electron cannot be seen by another F electron, which is at a far off place. So that means the conduction electrons are screening this F electron. And when this kind of screening happens, you will not see any magnetism. So in the previous case, the RKKY interaction, the conduction electron mediates magnetism. In this case, the conduction electron does not induce any magnetism here. It just stops the magnetism. So this is called Kondo effect. So there is always a competition between RKKY interaction and Kondo effect. If RKKY interaction is winning, the sample will become magnet. If the Kondo effect is winning, the sample will become a non-magnet. So this is quite often seen in these kind of rare earth based intermetallic systems, and this is quite studied quite extensively. And so if you see that in the previous thing, so the top one, the top graph is the RKKY interaction, the system behaves magnetically. The bottom one is the Kondo effect. At one point, you see that RKKY interaction and the Kondo interaction are equal and opposite. So that point, you see a quantum critical point. So this is quantum critical point means it does not know whether it can order magnetically or it cannot order magnetically. So this kind of quantum critical point appears at sufficiently low temperature and you see superconductivity in this. So by studying this superconductivity, one can know the mechanism of superconductivity so we can predict some new materials which can exhibit superconductivity. Okay, so these are some of the examples of samples which are showing quantum critical point behavior. So, but my main highlight today is how to grow single crystals of these intermetallic. So let me switch back again to crystal growth. And these are the various techniques. If you look into any literature about how to grow crystals, this is one of the standard figures that you would see. the crystals can be grown by these kind of various methods. So if you look at this, but first is the solution growth method. One of the oldest growth techniques, seawater, it becomes salt, it evaporates salt. So if you make any saturated solution and allow it to cool down very slowly, you will get single crystals. And the other one is melt growth. You take the sample to its liquid state by heating. Then you can get the single crystals by employing these kind of different growth techniques. And vapor growth. So how do some of the materials become sublime at some before melting, and some materials even after melting it will have high pressure, so you can grow the single crystals by vapor growth. So these are the various techniques. So all of them, to grow a single crystal, you need to take it to its liquid state and then do some process so that you get a single crystal. And sometimes you don't need to take it to its melting point. Some of the compounds are very difficult to grow. So it may not grow whatever may be the method that you adopt. So those cases, we can try to grow these crystals by solid state recrystallization. You keep it to its melting point, very close to the melting point, keep it there for about 6 months or so, then you can see the grain growths. That means the two grains diffuse together and then they form a larger grain. So you can get a single crystal based on that. So this is a solid state growth. In our lab, we have these kind of facilities. In my lab in Tata Institute of Fundamental Research, we have the facility to grow the crystals by Sokolowski method, by flux growth method, and by Bridgman method, and by vapor transport. So these are some of the partial list of the crystals that we have grown in our lab, and we have studied the anisotropic physical properties. So, although there are many methods available, how to choose which method of crystal growth I employ to grow a crystal? So to choose the method of crystal growth, you need to know some basic information about the phase diagrams. So the phase diagrams are which shows the regions of solid and liquid. Like as in maps, you see the regions of solid and liquids. So phase diagrams are useful to find out where exactly the samples are melting and where exactly the samples are solid. So I'm just going to give you a recap of your binary phase diagram that you have studied in your chemistry classes or even in 12th standard. So this binary phase diagram. This is a compound A, element A and element B. If you see this kind of phase diagram, then we say that it is a solid solution. Solid solution. If you imagine how can a solid be a solution? So it's a solid solution. This phase diagram is called solid solution. So what here it means that the sample A melts at particular temperature and sample B melts at particular temperature. If you dope A to B, in the crystal structure, some of the A atoms will be removed and the B atoms will be placed there. No new crystal structure will be formed. That means you can dope any quantity of A in B, or you can dope any quantity of B in A. That's it. You start with A, you keep on adding B, no new compounds will be formed. But you can do it as a kind of dopant or substitution or something like that. So this is what is the binary phase diagram, which explains about the solid solution. So just to show you, earlier I was telling A and B. Here I am giving a real life example. Germanium melts at around 960 degrees centigrade. Silicon melts at around 1400 degrees centigrade. You can replace germanium with any quantity of silicon, or you can replace silicon with any quantity of germanium. The structure remains the same. Only the germanium atoms are replaced by silicon, or silicon atoms are replaced by germanium. On the other hand, if you see silicon and carbon, you can see as you increase the concentration of carbon, at a particular composition, you can see the silicon carbide phase is starting. That means some new compounds are formed. So this, we cannot say this as a solid solution. So this is a new compound is forming. So, and this is also, it is not congruently melting. It is incongruently melting. So we have to choose the crystal growth method accordingly. So this is again another interesting phase diagram. You know, gold melts at 1050 degrees centigrade. Silicon melts at 1400 degrees centigrade. When you take the composition as gold 80 and silicon 20, you can see that the melting point comes down to 360 degrees centigrade. So this is called eutectic. Eutectic means low melting. So the gold and silicon for a particular composition, it shows a very low melting point. And this is quite often used in some ohmic contacts in devices in semiconductor industry. This is quite extensively used, which gives you some low resistance. Okay, so this phase diagram explains you all the concepts, all the technical terms in any phase diagram studies. Like for example, the above the region which is marked L means it's completely liquid in that region. For that temperature above that composition, you have completely liquid composition. And then around 952 degrees centigrade, 50-50, the 1:1 composition of silver and neodymium melts at around 952 degrees centigrade. So that means beyond 952, it will be a completely liquid. And that means this composition of silver and neodymium can be grown directly from its melt. That means I can use either Bridgman method or I can use Sukrotsky method to grow this crystal. On the other hand, Ag2Nd, you can see that it dissociates at 825 degrees centigrade. So that point is called incongruent melting point. So that cannot be directly grown from its melt. And if we come to the right hand side, just on the right hand side of silver neodymium, I see the two phase regions. So in the large region, you have liquid plus solid, which is coexisting. So I can use this eutectic composition as a flux to grow this silver neodymium composition, or I can grow this directly from the Sukrotsky method. So depending on the method which I wanted to adopt, I can choose the crystal growth method. Okay, so this is the Bridgman method. This is one of the very popular methods to grow crystals which has low melting point. Low melting point I mean by less than 1000 degrees centigrade. So the method is very simple. Materials which melt congruently can be grown by this method. For this, you need to have a two-zone furnace, and you can take the material in a sharp tip ampule, which is shown there. And this sharp tip initially is kept in the hot zone, just above the red line. Make sure that the sample is completely melted, and you translate it very, very slowly. So then you can get single crystals because the nucleation happens at the tip of the crystal, and as you pull it down, you can grow this crystal into a larger crystal. So this is one way of growing this crystal, and this is by translating. So now you can also take advantage of the temperature gradient in the furnace. You make a gradient in the furnace, so without even translating, just by reducing the furnace, you can have the gradient, temperature gradient in the furnace. Based on that, you can grow this crystal. So that is called a modified Bridgman or a vertical gradient freeze technique. So high quality single crystals of germanium has been grown by this Bridgman method. Germanium melts at 960 degrees centigrade, and you can see that the beautiful germanium single crystals have been grown. These germanium single crystals are used as radiation detectors, and these are very, very important. And if you have this kind of 5 to 6 kilograms of germanium, it's worth few lakhs of rupees, few tens of lakhs of rupees. Okay, so now we have grown this single crystal of bismuth in our lab, which is a high quality crystal. You know that bismuth melts at very low temperature, around 270 degrees centigrade it melts. But we have grown this crystal of bismuth by employing the Bridgman method, and we have studied the physical properties of this compound. One of my colleagues who predicted that bismuth will show superconductivity at sufficiently low temperature. Sufficiently low temperature means very close to absolute zero. You know, absolute zero is not reachable. 0 Kelvin is not reachable. So, but in Tata in our institute, we could go down to 36 microkelvin, 36 into 10 power minus 6 Kelvin. So it's almost very close to zero. The challenge there is to measure the temperature itself is a big challenge. So we have used NMR thermometers to measure the temperature of this microkelvin fridge. And then we found that superconductivity of bismuth appears at 0.53 millikelvin. That means 530 microkelvin. And the interesting thing is that theoretically, bismuth has been found to exhibit superconductivity in the nanokelvin temperature range. That means 10 power minus 9 Kelvin. But experimentally, we observed it at 10 power minus 6 Kelvin. That means 3 orders of magnitude higher. Experimentally, we have observed the superconductivity of bismuth 3 orders of magnitude higher than predicted by theoretical. So that means large number of theoreticians jumped into this, and then they wanted to investigate to understand the mechanism behind this one. Because if you know the mechanism of superconductivity in bismuth, then you can try to design some materials or predict some materials which have room temperature superconductivity or close to room temperature superconductivity, so that we can take advantage of this superconductivity effect and we can try to make some applications. But still lots of research is going on in this field. And so, as I told you, my interest is on magnetism related thing, and cerium is one of the magnetic compound, as you know, just now I explained to you, because there is one F electron which is unpaired, and it shows magnetism. We wanted to grow the single crystal of cerium magnesium 3. So if I want to grow the cerium magnesium 3, first I look at the binary phase diagram of cerium and magnesium, and I find that it melts at 796 degrees centigrade. That means it melts at 800 degrees centigrade. So now I can employ Bridgman growth to grow this crystal. So this is the technique which I have used. I have this Bridgman furnace where I have taken the material in a sharp tip ampule and then did some temperature profile, and I got single crystals. So for that, it's not a very simple task. Magnesium reacts with quartz. So I have to seal it in a metallic crucible. So I have sealed it in a molybdenum crucible. The material to be crystallized I have taken in a sharp tip alumina crucible, which is sealed inside a molybdenum tube. And this molybdenum tube is further sealed in a quartz ampule, because at elevated temperature, metals get oxidized. So this molybdenum will get oxidized if I don't use a quartz tube. So that is what is happening there. I have sealed this molybdenum crucible. The molybdenum crucible, inside the molybdenum crucible, we have the alumina crucible, inside which we have cerium and magnesium. And I did the temperature profile like this, from 0 to 800 degrees centigrade in about 72 hours, and then kept there for 24 hours. And by slowly cooling it, I got this, the bottom one, which shows that. So if I show this one, you have seen beautiful crystals of aluminum oxide, which are showing very beautiful jewelry-like crystals. But this does not look like a crystal. So you will not accept that it is a crystal. But I have already explained to you anything which produce diffraction spots or single crystalline. So the first thing I did was, I did an X-ray Lowe diffraction, and the bottom one shows the diffraction pattern. It shows a beautiful diffraction pattern, which confirms that this is a single crystal. So before I did the Lowe diffraction, I have also done a powder X-ray diffraction, and I have found out the phase purity. That means whether there is any impurity phase, whether there is any unreacted cerium or unreacted magnesium or any other composition of cerium magnesium has formed in my sample. So all those things can be confirmed from the powder X-ray diffraction. And on the other hand, if I do X-ray diffraction pattern using that instrument which is shown above, it uses a polychromatic source of X-ray. And this is a very interesting question. For the powder X-ray diffraction, we are using a monochromatic X-ray. For X-ray diffraction using Lowe method, we use a polychromatic source. Because there theta is varying, here theta is fixed. You know the Bragg condition, 2d sine theta equal to n lambda. So whenever 2d sine theta equal to n lambda is satisfied, in the powder X-ray diffraction, lambda is fixed, theta is varying. So whenever the condition is satisfied, you will see a peak in the powder X-ray diffraction. Whereas in the case of Lowe diffraction, the spots are appearing whenever the condition 2d sine theta equal to n lambda is satisfied. But here, lambda is varying, theta is fixed. So this is a very good, interesting interview question, or even a entrance exam question, something like that. Okay, so we have studied the magnetic property. We did the susceptibility measurement from room temperature to 2 Kelvin, less than around 2 Kelvin. We saw that it is showing a Neal temperature, magnetic temperature around 2.6 Kelvin. And some of you, if you have studied magnetism, you might have studied about Curie-Weiss law. So chi equal to C by T minus theta B, it's a very famous well-known formula. From that, we can calculate the effective magnetic moment. With the value of the effective magnetic moment, you can say something about the valency of this rare earth. So this here, the value is mu effective is 2.61, which is very close to the effective magnetic moment of cerium, which is 2.54 mu. So then we can say that the cerium is in trivalent state. And we can also see that the saturation magnetization. I am at a temperature much below the antiferromagnetic ordinary temperature of this compound, which is 1.8 Kelvin. And I see the effect of magnetization versus magnetic field, and I see the magnetization is increasing. It is not increasing to the value of 2.14 mu B, which is the saturation moment for cerium. we have reached only 0.5 MeV at 12 Tesla. So that is something which is interesting happening. I'm not going to go into the details of that because I want to focus on the crystal growth aspects of this one. So that reduced moment is because of this Kondo effect, which I have already described. Okay, so now this is about the Bridgman method. Now the interesting, most advanced crystal growth method, which is called Czochralski method. So, so that is the Czochralski method is quite an interesting story. So Czochralski, he was born in Poland and he was doing his undergraduate in Germany. So this is during the World War time. So the German, the government wanted to find out some interesting new metallic samples. So his job was to melt some metallic samples and solidify it and study the microstructures. So he was doing these low melting metals like tin, indium, bismuth. These are melting around 300 Kelvin or some 300 degrees centigrade or something like that. So he was just melting these materials and then solidifying it very rapidly. Then he is observing it under microscope to find out the microstructure, whether it is hard enough to be used for some other applications and things like that. So in those days, you have to use this ink pot. You touch the ink pot and you can write down the notes. So you can see that his furnace is a very small furnace. It's a very small crucible. He was melting tin and then the ink pot was kept very near to the furnace. Instead of putting his pen into the ink pot, he put it in the furnace where there was a molten tin was there. He realized the mistake and he took out the pen very quickly. A string of tin came along with the pen. And he found that quite interesting. So he did an X-ray diffraction of that. And he found out spots. So I told you anything where you get a diffraction spot is single crystal. So he found out that the tin samples can be grown by slowly cooling it. So then he designed the one which is shown on the left-hand side, 1917. He designed that furnace to melt a metal, insert a seed crystal, and slowly pull it out. So you can get single crystals of these materials. So that was in 1917. And 1950, this more sophisticated instrument has been developed. And you can rotate the crucible, you can insert a seed crystal and then slowly pull the crystal. You can rotate the seed in one direction and the crucible in the other direction. These kind of advantages has happened. And in today, silicon single crystals are grown by this very sophisticated crystal puller, which is shown here. And crystal growth of these kind of device quality crystals are very, very important in the sense that a large amount of money is being spent on that. First of all, the power and the purity of the material which is being used. So before going for the crystal growth, they do the simulation and then they understand the physical, how the crystal growth will proceed, and based on that, they grow the crystals. So the crystal growth will be in a huge building which is completely vibration isolated, and then you keep the controller in another room, and then you try to control the crystal growth process from other building. So that is the kind of crystal growth. That is the Czochralski method. And we have a furnace in our lab to grow intermetallic compounds by Czochralski method. So we don't have much larger furnace. It's a very small furnace where we can melt about 10 to 15 grams of sample. And here we use these electric arcs to melt the sample. So the left side figure shows that there are 4 electric electrodes, 1, 2, 3, 4, which are nothing but thoriated tungsten rods. You pass a huge current to these tungsten rods. These tungsten rods will make a arc, and from that you can melt the samples. So you can melt the samples whose melting points are as high as 3000 degrees centigrade in that. So when I put the chamber down and I strike the arc, I can reach temperature as high as 3000 degrees centigrade. So this is the basic principle there. You take the material in a hearth. This is called copper hearth, the brown colored stuff. In the middle figure, that is the blue colored one, which is water cooled. The copper has a high thermal conductivity, but it melts at 1000 degrees centigrade. So, but I can hold a metal whose melting point is 3000 degrees centigrade in a copper hearth, because since copper is highly conducting, the heat will be taken away by the water and the copper will not melt. So that's how I can melt the samples whose melting points are very high using the 4 electrodes, and I melt the sample multiple times, make the sample homogeneous, and then cut a polycrystalline sample and insert the polycrystalline sample into this molten solution. The seed crystal is coming from room temperature. Here the sample temperature is say 1500 degrees centigrade or 1600 degrees centigrade. When I insert the seed crystal, there will be a local solidification because of huge gradient. And when there is a local solidification, it will form lots of polycrystals, like the bottom one. The various grains are shown. And I do a small necking process so that I allow only one grain to grow into a single crystal. So this is how the crystal growth, during the crystal growth, it looks like this on the right hand side. And you can see that the crystal cooling speed is about 10 to 15 mm per hour. And this is one of the crystals which we have grown very long time ago. So we have used a polycrystalline seed, and I can see that at the center it comes a very small diameter, and then the diameter increases. This small diameter is for necking. I mean, I select only one grain to grow into a larger crystal there. And this is a sample which exhibits superconductivity at around 5.7 Kelvin. It also shows some other kind of transition which is called charge density wave transition at around high temperatures around 74 Kelvin. And you can see that the anisotropy. If I pass the current along the A axis, the resistivity is about 200 microohm centimeter there, and along the C axis it's about 50 microohm centimeter. So to study these kind of anisotropic properties, these single crystals are highly useful. And this is one of the recent crystals that we have grown. These forms under these semi-metallic systems. Again, you see that the MOSI2, which is melting at around 2080 degrees centigrade, which is on the right hand side. And again, the same process, we made a polycrystalline sample, we cut a seed crystal, and then insert the seed crystal and slowly pulled it. And we got beautiful textbook-like lava pattern. So this compound crystallizes in a tetragonal crystal structure, and this is along the A axis and that is along the C axis, the lava diffraction pattern. So we have found out a beautiful lava diffraction. This, just by looking at the lava diffraction pattern itself, I can say that the crystal that I have grown is of highest quality. The quality of the crystal is extremely good. And that is further substantiated by measuring the electrical resistivity. So the top one, you can see that at room temperature, the electrical resistance is about around, that's in the log scale, about 50 microohm centimeter, and at a very low temperature, around 2 Kelvin, it's of the order of something around nano ohms or something like that. So if I calculate the residual resistivity ratio, RRR, which is defined as rho 300 divided by rho 2 Kelvin, that gives me a number which is 4000. That 4000 tells me that it is an extremely high quality single crystal. When I say that it is an extremely high quality single crystal, if I do this magnetization by ramping up the magnetic field, I can see quantum oscillations. So these oscillations are appearing because of the Fermi surface. So we can know these are metallic systems, and then we can know the Fermi surface properties by doing this magnetization versus magnetic field, by ramping the magnetic field, by studying the oscillations, quantum oscillations, we can know the information about the Fermi surface. Any metal has a Fermi surface. To know the physical properties of this Fermi surface, these kind of oscillation studies will be highly useful. This is called Dihas-Van Alphen effect. And these oscillations will be seen only in high quality single crystals. Of course, if you go back and check your solid state physics book, you can find out this Dihas-Van Alphen effect, or DHVA, which tells you about the Fermi surface properties. So now, growth from low temperature solution. So we can grow the single crystals by, I told you, to grow a crystal, you need to take it to its liquid state. To tell you in a very naive example, sodium chloride, which melts at around 800 degrees centigrade. But if I say that I don't need to take sodium chloride to 800 degrees centigrade to grow a crystal. I can grow the sodium chloride crystal at room temperature. You may be a little bit surprised. You have to take it to the liquid state. But I can grow although the melting point of sodium chloride is 800, I can grow the crystal at room temperature. How? I can dissolve sodium chloride in water and I can take it to its liquid state. And by making a supersaturated solution and slowly decreasing the temperature, I can get the single crystals. So even though if a material has a very high temperature, you don't need to take it to its melting point. Instead, if you know where it can solve, in which material it can dissolve, then taking advantage of the solubility, you can grow the single crystals by solution growth technique. But metals do not dissolve in water. So you have to find out other suitable solvent. So this is what a simple example where you can do it in your home. You can go to your home, take a beaker or some glass, dissolve some sodium chloride into that, heat it up a little bit, add more sodium chloride, you will get a super saturated solution. You decrease the temperature, you don't need to do anything, you leave the solution as it is. Lots of crystallization will happen at the bottom of the beaker or tumbler, and then you pick one of the crystals, again make another super saturated solution, tie a thread into the super saturated solution. From the second day, you will see the crystal which is growing into a larger, as I have shown you here. So it's a very simple tabletop experiments one can play with. You can do it with sugar, but the solubility of sugar is not so good as sodium chloride. Sodium chloride will be an ideal choice, not the iodized one. If you can get that rock salt kind of thing, that will be helpful. Okay, so sodium, this kind of low temperature solution growth are useful for materials which are soluble in water. So most of the NLO crystals can be grown by this method. So you can see that crystals of huge sizes can be grown. So these are useful in laser applications where you can generate lasers using these crystals. You can see that guy who is cutting a huge crystal, after aligning the crystal using this law of diffraction, he cuts it along a particular crystallographic direction. Okay, so now, as I told you, I'm not working on any nonlinear optical crystals, I'm working on intermetallic systems. So I can grow these intermetallic crystals by dissolving it in some solvent. So in the case of metals, I cannot take the metal in a beaker and heat it to 1000 degrees. Beaker will melt at some 300, 400 degrees centigrade. So I have to look for a suitable material where I can hold this one. So for that, this aluminum oxide is useful. This aluminum oxide crucibles, I can use that to hold these metallic samples. See, metals do not react with oxides. Oxides react with oxides easily. So when I want to grow a metallic crystal, I have to use an oxide crucible. On the other hand, when I want to grow an oxide crystal, I have to use a metallic crucible. So why metallic crucible? Because platinum is one of the noble metals. It doesn't get oxidized at elevated temperature. So if I want to grow an oxide material, I can take platinum crucible, put the oxide material into that and try to grow that crystal. So here, all these crystals are grown using this alumina crucible. I mean, I take the material in alumina crucible, seal it inside a quartz ampule because any metal at elevated temperature gets oxidized. So I have to seal it in a quartz ampule. So that's what I will show you. So these are some of these low melting, the one which has red colored thing, these have low melting point. Like for example, bismuth, lead, these are having low melting around 300 degrees centigrade. If I go to aluminum or antimony, they are having a melting point around 650 degrees centigrade. I can take advantage of this low melting point of these metals and I can use them as a flux to grow the single crystals which I am interested in. For example, in this binary phase diagram, cerium antimony 2. Antimony melts at around 650 degrees centigrade. If I take a large quantity of this antimony, that means cerium 1 and antimony in the 20 mole %, in this region where I have shown, in that region you have liquid of antimony and a solid of cerium antimony 2. So by doing a proper temperature profile, I can get the single crystals of cerium antimony 2. So this is the temperature profile that I have used. Typically I cool it at the rate of 1 degree centigrade per hour. That means the growth process is about 1 month or 20 to 22 days or something like that. Roughly the total growth period is about 20 days to grow a crystal. So during this process, there should not be any power failure. If there is a power failure, then you will lose the entire material or you will get a very tiny crystals. So this is we have grown this single crystal of cerium silver 2 and germanium 2. So in this case, none of the individual elements has a low melting point. Cerium has around 900 degrees centigrade. Silver is also having around 950 degrees centigrade melting point. Germanium also 960 degree melting point. But when I look at the binary phase diagram of silver and germanium, I found out that it is melting at 650 degrees centigrade. It has a eutectic composition at 650 degrees centigrade. So I have taken advantage of that eutectic composition to grow this crystal of cerium silver to germanium 2. And so now the question is that this compound has a eutectic temperature at around 650 degrees centigrade. After I did the temperature profile like this, I have come down to room temperature. So now inside the crucible, I have my solid flux inside which I have lots of crystals. Then how do I separate these crystals? If I break it, I will break the crystals as well. So for that, we know the melting point of this eutectic composition is 650 degrees centigrade. I heat up to 750 degrees centigrade and take it out, this ampule from the furnace, put it upside down in a centrifuge, and I spin the centrifuge at a very fast speed so that the liquid comes out, the crystal still remains inside the crucible, so I can separate out the crystal. So these are the crystals that we have obtained, and the first thing we do is the Lowey diffraction to find out if it is a good single crystal, and this diffraction pattern confirms that they are crystalline, single crystalline, and we have studied the anisotropic property. So depending on the material's property, we have to adopt a different temperature profile. For example, in this case, cerium cobalt indium 5, which is a heavy fermion superconductor, was quite extensively studied in single crystal form. I have cooled down at 6 hours, some 100 degrees in 6 hours, and then I have cooled down very slowly. So these kind of temperature profile, depending on our experience or from the literature studies, we employ different growth profile, temperature profile, and we grow the single crystals of the material that we wanted to make. You can see the nice superconducting drop at 2.3 Kelvin, the inside of this figure, where the electrical resistance drops very rapidly at 2.3 Kelvin, confirms the superconductivity in this sample. Okay, so there are growth morphologies. When the crystal is growing inside a solution without any constraint, then it will have a well-defined morphology. So this is true for sodium chloride also. If you try to grow sodium chloride in your home, then it will have well-developed facets. So that means depending on the space group and the lattice constant of the material, you can easily predict their morphology. So for example, tetragonal compounds crystallizing in the tetragonal crystal structure will have a platelet-like morphology. Compound which has an orthorhombic crystal structure will have a needle-like morphology. Hexagonal crystals will have a hexagonal crystal-like morphology. So depending on the space group and the lattice constant, you will have different morphologies. So for a cubic, sometimes you will end up with this kind of triangular pattern. That is because how the growth units are attached to the crystal. So initially the single nucleation happens and a large crystal grows, and the next nucleation happens, a step arises. Inside the step you have some kink, and the kink are the most preferred places for the growth units to get attached. And if you see this right hand side figure, the K is the kink space, and S is a step, and the F is the flat. The growth units would like to go and sit at the K sides so that it grows into a larger crystal, and you will see this kind of triangular pattern as I have seen in the, as we have observed in the bottom figures. Okay, so then some of the crystals, they don't melt, they sublime. So in those cases, we can take advantage of their sublimation procedure, and we can grow these crystals by keeping at two different temperatures, hot zone and cold zone. In the hot zone, the sample gets evaporated and gets transported to the cold zone, and you get the single crystals by this process. This is called physical vapor transport. And sometimes you use a transporting agent like iodine, bromine, or something like that. This chemical transporting agent will also take the material from the hot zone to cold zone, and you can get some crystals. The most interesting thing, in our body we have lots of crystals that's being grown. So that is because, as I told you, any supersaturated solution, when it deposits as a single crystal. So all these urinary stones, gallbladder stones are nothing but because of the deposits of supersaturated solutions. So it is better to drink lots of water so that these kind of supersaturation can be avoided, and you can be free from these kind of urinary stones or called calcium oxalate and calcium phosphate crystals that grow in your body. So the take-home message, I'm not concluding anything, the take-home message is that crystals can be grown by a variety of methods, and these are the different techniques that I have explained to you. And if you are interested, based on my idea, that you can try growing sodium chloride crystals in your home and see for yourself how the crystal grows. Thank you very much. More than happy to. Yeah. Powder X-ray diffraction. So that is the, see, because single crystal XRD, we are using it only for finding the crystallographic direction. That means we are using law-wave method. But the single crystal X-ray diffraction is to solve the crystal structure. We are not interested in solving the crystal structure. So our aim is to find the crystallographic direction. We are growing the crystal. We don't know which crystallographic direction is there. So we use law-wave diffraction method to find out the orientation of the crystal and cut the crystal. For lattice parameters, we use powder X-ray diffraction. So that is more simpler because we are not working on new systems. We are working on systems which are already existing. So we know the lattice constant. So from the powder XRD, you can easily confirm that.
Thank you very much for the lucid explanation of various techniques involved in the growth of crystals. Now, my question is a very layman's question. You have explained various methods which are employed in growing crystals of different kinds. Now, is there any specific method which you try to improve to a large extent by which we can get some benefit for some contemporary requirements? So, of course, your domain, now what you have touched is the various techniques of growing crystals and elaborately you explain. And you can go on improving in any technique as
Yes.
But any specific example can you think of that your techniques are used extensively in producing any specific class of crystals in India?
Okay, so within the country, not in my lab because I am into fundamental research aspects.
Yes.
But in BRC and RRCAT, they are growing these laser crystals. That the huge crystal, transparent crystals which I have shown into you, non-linear optical crystal. They are growing large size crystals.
For specific purposes.
Yeah, that is for laser application. And in BRC, the neutron detections. So they are growing their own crystals because for neutron BRC they don't sell the radiation detectors.
Yes.
So they have to make their own. So they are making. Yesterday also I was in BRC where they are going to have a patent now where they can detect neutrons and gamma rays. So they have made their own devices. So that is possible. So our mandate is to totally different. Even in our institute, there are high energy physics people who wanted to make this lead tungstate crystal. So the lead tungstate is a very good scintillating material. So, but with the facility that I have, it may not be possible. But if you have the facility, then we can grow the crystals. Thank you.
From a research scholar as well, and I'm working on non-linear optics. So, and I want to know, does non-linear optic in the field of crystal growth, the crystal growth in the field of non-linear optics still has the importance since thin films are taking the lead. So crystals are playing an important role on the thin films. So that's my question.
That's a very good question. See, for example, in the case of non-linear optics, still people have to grow good quality crystals. They can't use thin films for this NLO application. So still, to my knowledge, you need to have a high quality crystal. So most of the non-linear optical crystals can be grown by dissolving it in water. So some of these organic crystals like DAST or something like that, they are soluble in some organic solvents, but the difficulty there is that they are not stable at room temperature. So you have to give some protective coating for that. So when you put a protective coating, then your optical experiments will not be that useful for that. So you have to, one has to determine some new materials where the materials are very stable at ambient conditions, then that will be good for you.
Since I'm working on the same, what I just said, I'm just combining organic with inorganic materials. So the idea, what the doubt we have is the doping. In your case, you just said
Doping with metal and metal.
Yeah.
Till a particular place, you can understand that doping is when after some point it undergoes some reaction, they form intermetallic
Yes.
compound. So in my case, organic and inorganic metal, I really don't understand where exactly it forms, it gets doped or not. So how do I confirm whether there is doping case?
So that, see, one of the ways is that you can do a single crystal X-ray diffraction. So suppose you don't put a doping and you expect it to be replaced by at some point. Some molecule is going and sitting and attached to that. So you can easily find out from the crystal structure whether the dopant has gone into the crystal lattice or it is somewhere lying outside or something. If we don't have it as a single crystal, it can be on the grain boundaries. So, but finding the crystal structure of organic compounds is relatively difficult because the hydrogen atom positions are difficult to find out. You have to do neutron diffraction experiments. So you can submit your research proposal to DRC. If you have some crystal and you expect that you have put in some dopant and you want to find out whether the dopant has gone in and the structure of your organic element, the best way is to do a neutron diffraction, find out the crystal structure, and that will tell you when. And there are lots of, in BRC, these kind of proposals are very easily accepted and you can do these crystal structures. Yeah.
Thank you, sir. Thank you for the information.
Appear in the polycrystals rather than in the single crystal?
That's a very good question because these are ceramic materials and we don't have a proper solvent or because these melts incongruently. When you take it to its melting point and you cool down, multiple phases form. So you have to dissolve it in some solvent and grow this crystal. So one of the famous solvents is that the constant element copper oxide or bismuth oxide, copper oxide eutectic composition. So these are the things which we have used, people have used also, and they have grown the single crystal, but single crystals are very tiny. But there is another new technique which people have used, this optical floating zone. They make a feed rod and a seed rod, and they grow the single crystal. But these are not completely single crystals. There are some large grains which have been grown. But growing a large size highly single crystals is impossible. That is because of the material problem.
I am Dr. Arumugam, HOD, Department for Electronics and Aloysius College. I want to make some experiences here. And finally, I will lead you question. I have been growing crystal in my work in PhD work in crystal. To begin with, as you suggested, we started with the sodium chloride and the inorganic crystals. We used to get good crystals, bigger crystals. And if I go for second harmonic coefficient and all, the efficiency is less. As we move on to semi-organic, good crystals, medium group crystals, and we increase SH efficiency, TH efficiency. And further, we published. And as we go on, we found that many organic papers, materials of organic materials. Thousands of papers are coming. And we are not able to grow the crystals. Big crystals, difficult. But efficiency, everything is high. So what, if I produce 10 semi-organic crystals, my research mates used to develop thousands of these papers. And I want to know the status of these crystals now, because I have been doing it in 2008 and it is so many papers are produced. And what is the application, sir? Application, I want to have a just brief survey and just one kind of thing.
As I told you, one of the main difficulties is that organic compounds are not so stable at ambient conditions. So they are, but on the other hand, there are many papers which publish I know there are few papers, they have, many of these Indian papers have been cited that there are something wrong with the answer. Seriously, I'm telling you that. There is a critic, particularly on this NLO material, they say that it is non-centrosymmetric, and then our centrosymmetric, it doesn't produce, it shows NLO material, NLO property or something like that. But mostly from the southern part of India, there are lots of NLO papers which have been predicted to be wrong. I can give you I have it in my computer that some Poland, the professor from Poland, as you have rightly pointed out, thousands of papers are coming on this one. But sometimes they get published just like that. But these are the difficulties which he did not find, he did not say that it is a wrong or something like that. These are the difficulties that I find in understanding these kind of papers. That is the comment that he has made. But I don't know how to trust these things. But the NLO materials are really challenging materials. The most famous thing is that KDP, ADP. These are the most popular and which are quite extensively used. So other organic materials and this semi-organic or something like that, that I'm not sure about it because I'm totally working on a different. Yeah. Is some huge MEB or something. Yeah, I'm just talking about small. Very, very small. Yes. So the first point is that the F electrons, F shall start to begin to fill from for lanthanum there is 0 F electron, there is no F electron. For cerium there is 1 F electron. That means that 1 F electron is unpaired. You can see the first thing. There is 1 unpaired electron. S equal to half, L equal to 3. Based on Ohm's rule, L minus S is 5 by 2. And your landed splitting factor is Gj is 6 by 7. Your saturation moment will be Gj into J, which is 2.14, and this is 2.54. But the thing is that if you look at this is for cerium. The 4S wave function, you can see that the red colored curve, which is highly local. And suppose there is one 4S electron, and the other 4S cerium metal is sitting in the lattice like this. Let us say the lattice separation is 4 angstrom. The 4S wave function is only this much, and here it is only this much. They don't interact. They cannot interact because there are no overlap. Whereas 5D1 and 6s2, they can overlap. And we cannot distinguish between the 5D1 and 6s2 electron of this cerium atom or this cerium atom. It is indistinguishable. They become the conduction electron. So now, this is one F electron, this is another F electron. The small arrows are conduction electrons. So these F electron polarizes the conduction electron. One of the F electron surrounding the conduction electron, the F electron polarizes the conduction electron. That means there is some interaction is happening. That is called the exchange interaction. And this exchange interaction, if it is positive, then this conduction electron passes the information via the other conduction electron to the F electron. Let this order ferromagnetic. If this exchange interaction is negative, then it shows that we should follow this. So this is the theoretically predicted, and it has been very well experimentally observed in most of the cases. Kondo effect is this one. So this effect, not the conduction electron screens the conduction electron. Maybe the distance is much smaller, much larger. See, the bottom curve, that is at the 0 means the F electron side, and as we increase the next F electron is as a function of R. So there is one F electron, the other F electron is a function of R. Depending on the distance of this thing, you have this oscillatory pressure. So you can have either ferromagnetic or antiferromagnetic, ferromagnetic or antiferromagnetic. So that everything depends on that J, which is the exchange interaction. We don't have any control over the exchange interaction. We cannot tune the exchange interaction. We can tune it by applying pressure or something like that, or doping. But as such, we don't have any control. So I want to make a ferromagnetic material, I cannot design on my own. So it all depends on the exchange interaction. If it is positive, then it shows pepper. And for Kondo effect, so because the distance is much, much larger, then it forms a screen, conduction electron forms a screen, and the other electron. So then, if it is, this kind of charge cloud is forming in one of the 4F electrons, the other 4F electron cannot see this one, and there is no magnetism. It is not interacting with the next F electron because the conduction electron forms a cloud.
Any questions?
Thank you so much, sir, for the wonderful lecture that you have given us. We get a lot of insights, and we are so much means our interest towards crystal growth is really increasing, I could say. And I have a very simple question that you mentioned before, that organic compounds are not stable in ambient temperature. But if we would like to grow organic compounds in an ambient temperature, how can we adjust with this instability of these organic compounds so that we can get a good quality crystal of this compound?
If I know that, then I'll get some interesting award or something like that. See, the organic compounds are not stable. That is by nature. You keep acetone for some time in open air. You just evaporate. You just keep hexane, any organic material for that matter. It will just evaporate, and it also reacts with the ambient condition. So one of the ways is to put some protective coating on top of that, so that you can get advantage of this organic. But anyway, the efficiency will be very much more. If you are putting any protective environment, then your efficiency will be.
Thank you, sir.
So as I told, crystal growth is one of the fields where you can become an entrepreneur, and this is the right time. Really, I mean it, because there's lots of huge, large size single crystals are very, very important, particularly for solar cell applications. You know, there is, in India, we don't prepare this kind of large size silicon crystals or germanium crystals. Adani Group in Gujarat, they have just made a huge single, I mean, it's not a single crystal, it's a multi-crystalline silicon. Even multi-crystalline silicon is useful for making the solar cell applications. But there is lots of opening. But it's all depends on you whether you want to choose, whether you want to become an entrepreneur so that you can choose crystal growth as your topic of this. Okay, this is kind of advertisement, I would say.
Sir, how to get into TAFR for PhD and
Wow,
internship?
that's a very good question. I thought that I should add those things, but somehow I missed it. So we have a nationwide entrance test on the second Sunday of December every year. So anybody who has completed BSc can appear for the exam, but it will be of the MSc level questions. So it will be on the second Sunday of every year December. You have to complete your nationwide entrance test, followed by an interview. If you are successful with the entrance test, there is another interview which will be held in March. Last week we had our interview. And if you are successful in the interview, you can get into the TAFR. Now TAFR has a TAFR Hyderabad campus, TAFR Mumbai campus. TAFR Mumbai is the original TAFR campus. And we have TAFR Hyderabad, NCRA, National Center for Radio Astronomy in Pune, NCBS in Bangalore, ICTS in Bangalore. So ICTS is completely theoretical studies, NCBS is for biological studies, and for physics and chemistry, you have TAFR Hyderabad and TAFR. It's a tough competition, but if you are successful, then see, all that you need to understand the basics very thoroughly. So we try to investigate your basic understanding of physics and chemistry and things like that. So if you are successful, then so unlike with GATE or CSIR, we don't accept those. We have our own. Of course, I have, sorry, yes, sir. I have my, if you want to ask any questions, you have my email address here. Yes. Yeah, of course. See, suppose for example, you have grown a crystal and you want to do a directional dependent studies. My lab, everyday bread and butter is doing lobbying. all my graduate student who comes to my lab, the first thing he learns is how to orient a crystal along the crystallographic direction. So the first thing, once he learns that, he grows a crystal, he aligns it, and he does all the physical properties. And we have a very good terahertz lab. So suppose if your sample is terahertz emitting, or you want to do some experiments with terahertz, we have my my colleague who is working on this kind of thing. Because nonlinear optics, terahertz is one of the important experiments that we can do. So those kind of things can be done. So the thing is that you do your basic characterization, like confirm that you have a good quality crystal, then taking it to the next step is relatively simple. So, but the thing is that people have their own assignments and their own mandates to study their thing. And it may not be possible for you to bring some arbitrary crystal and ask them. If you do some basic confirmation of your sample, it belongs to this category, you are expecting this physical property from them, then it will be very, very much possible. I mean, TFR is open to this kind of collaborations.
Sir, one question regarding that dispute superconductor that you have in your lab, where the temperature that you have elevated to 3 orders.
Magnitude. Yeah.
Any study related that
Some people have come out with some theory, even from our math science. Professor G. Bhaskaran has come out with some theory, but theory is beyond my understanding, so I cannot comment it. But if somebody understands exactly what is the reason for that, there is a large possibility that we can bring it to Kelvin and then to increase the temperature further. It may not be. See, because all our strongly correlated systems, it has been studied exclusively for that purpose. See, these materials show superconductivity at low temperatures. At high temperatures, for example, high DC superconductors, they have phonons. Once you have phonons, it becomes very difficult for the theoreticians also to study this. But if you are having a superconductor at sufficiently low temperature, you can ignore phonons. And then you can concentrate only on the superconductivity aspects and try to understand. So even in that case, for material which showing, except for BCS superconductivity, the unconventional superconductors, there's no theory which can explain this.
Thank you, sir, for sharing your knowledge and insights. You have broadened our mind and deepened our understanding on the significance of crystal in various fields of technology. Now I request Dr. A.P. Radhakrishna for the concluding remarks.
Dear friends, probably my choice for this guest of chief guest. I have retired from the service. That is probably the reason for to invite me for this particular function as a chief guest. It is a wonderful talk by Professor Arumugam. Professor Prakash Karat, my teacher, way back in 1979, passed from the SSLC, joined to the Saint Philomena as a youth student. He inspired, he motivated not only me, the thousands of students. In that time, we had the physics, we called that physics as the solid state physics. Professor PPK taught us the classical mechanics and then the current electricity. I still remember his class. And in the Philomena, we had one particular setup, that is the earth inductor. We did a lot of experiment. The whole setup was done by Professor PPK. Unfortunately, now that particular experiment was taken out from the syllabus due to the difficulty of doing that experiment. But the experiment always should be there. These are the very intricate experiments which actually make the students to learn the basic of the doing the research. It's not so easy to develop the single crystal or the polycrystal, and a lot of the basic ideas should be there. The experimental, the footage should be there, and all that we will learn in the college level. And certainly your talk was so interesting, and so many questions were asked in the that indicate how much you have reached the audience. And usually the science, we say that it is a dramatic discovery or the serendipity. And your one particular experiment done by Zikrovsky method, and the probability that is the serendipity, like the discovery of radioactivity or the discovery of the X-ray, even the various other experiments. And lastly, you have said regarding the single crystal in case of a uric acid or the gallbladder stone, and that we have understood because we are coming to the next stage. And this is the beautiful type of the activity we are conducting in memory of our teacher, who is the motivator for all of us. And for the decennial celebration, 10 years we have conducted, and even in the COVID period, there is a 21, I have seen that, Chandrasekhar 21 and 22, and we could conduct this particular program that indicates the motivation for the students who got from the Professor Prakash P. Karat. Thank you for the opportunity given.
Today's event, I request Dr. Neelakantan Biki to propose the vote of thanks.
So I'm privileged, and I'm really grateful, and I'm really privileged to propose the vote of thanks. First of all, I would like to thank our Vice Chancellor, Reverend Dr. Praveen Marcus S.J. So he always is a motivation for us. So I thank Father for presiding over the function in this absence. I thank our chief guest and today's resource person, Professor Arumugam Thamizhavel, Professor and Chair, Department of Condensed Matter Physics and Materials Science, Tata Institute of Fundamental Research, Mumbai, for coming all the way from Mumbai and having enlightened us on isotopic studies of strongly correlated electron systems. Thank you very much. I now request Professor Prakash P. Karat to hand over a memento as a token of our love and appreciation. Thank you, Professor Karat. I thank our guest of honor, Dr. A.P. Radhakrishna, retired professor, Department of Physics, St. Philomena College, Puttur. So thank you for gracing the occasion. I thank Professor Prakash P. Karat, formerly Professor of Physics and former Controller of Examinations, Mangalore University, who is a mentor for all of us. Thank you very much. I thank the head of the Department of Physics, Dr. Ishwar Bhatt, for taking the lead and welcoming all. Thank you. I take this opportunity to thank Dr. Chandrasekhar Shetty, who has worked tirelessly for this lecture to happen. It was his great child to begin with an endowment lecture in the name of Professor Prakash. Thank you very much, sir. I acknowledge the presence of Professor Chandrasekhar Shetty, Professor K. M. Balakrishna, Professor Manjunath Patabi, Professor K. B. Vijay Kumar, Professor K. V. Rao, Professor Ganesh Sanjeev, Professor G. G. Prabhu, and all other professors, retired, and other teachers from all the neighboring colleges. I thank you all for your gracious presence. Thank you very much. I thank faculty members, co-faculty members from our college. Thank you very much, sir, sirs and madams, and also research scholars for gracing the occasion. I thank our students for having attended the lecture. Thank you. I also thank the press and media for their coverage. Thank you very much.
When we thought of making a book, there are 10 authors who wrote the book. I request the authors to collect a copy from Prof Prakash P. Karat. I request Dr. Jeevan Pinto collect a copy from sir. Dr. Deepak is here. Neelakantan is here. Yeah. Dr. Kumar. Some of our authors are in US, some of them are in various other countries, and two of others went to the NSS program. They were NSS officers. They have an award ceremony there, therefore they will be felicitating there. Therefore they left. Now it's the time for this book. We have made few copies of the books. It is not for sale, but the students can get it paying the printing cost of 200 rupees. Again, that will go to the endowment fund. Now we have the refreshment outside.